Hey everyone, and welcome. Today, we're diving into one of the absolute biggest questions in all of science, the hunt for a theory of everything. You know, that single beautiful idea that could explain the entire universe, from the tiniest particle all the way up to the biggest galaxy.
But what if the answer has been staring us in the face this whole time? I mean, think about it. What if the wild, reality-bending physics of black holes and the super strange rules of quantum mechanics weren't two different books, but just two chapters of the same story? What if the biggest, most massive things in the universe and the absolute smallest were actually, deep down, the exact same thing?
So before we can even get into that, you have to understand the massive challenge physicists are facing. See, this quest for a unified theory, it isn't just one problem to solve. It's actually two completely separate, gigantic hurdles that we have to clear first. We've basically got to build two different bridges before we can even think about connecting them in the middle.
Okay, so here are the two paths. On one side, you have the world of the heavy, the cosmic, galactic scale. The big challenge here is getting Einstein's theory of gravity to play nice with his theory of special relativity. Then, on the other side, you have the world of the light, the tiny, subatomic scale. And the goal there? To get the bizarre world of quantum mechanics to work with that same theory of special relativity. So, let's take these on one at a time, shall we? First up, let's talk cosmic heavyweights. For this, I want you to imagine gravity not as some force that just pulls you down, but as the very fabric of space and time flowing, kind of like water swirling down a drain. And in this world, the most extreme objects aren't just big. They are so incredibly dense, they literally break reality as we know it. Yeah, we're talking about black holes. Now, the absolute key to understanding a black hole is this idea of an event horizon. It's not a physical thing you could touch or bump into. It's an invisible boundary. It's the exact point where space itself is falling inward faster than the speed of light. And since nothing, absolutely nothing, can go faster than light, anything that crosses that line is trapped for good, even light itself. All right, so you know what? Let's go on a little trip. We're going to fly right up to the simplest kind of black hole there is, a non-spinning one. The type Karl Schwarzschild first figured out just a few weeks after Einstein published his theory of general relativity. So yeah, buckle up. As we get closer, reality starts to get, well, really weird. When we're far away, things orbit in nice, normal ellipses, just like you'd expect. But as we get closer, gravity bends light so much that orbits start to wobble in this strange, beautiful daisy pattern. Get even closer, and you can't even have a stable circular orbit anymore. Then, you hit this truly bizarre zone where even photons, particles of light, can get temporarily trapped, orbiting the black hole. And finally, the horizon. From the outside, it would look like your time grinds to a complete halt right as you cross that point of no return. But what if the black hole is spinning? Well, in 1964, a guy named Roy Kerr figured that out. A spinning black hole literally drags the fabric of space-time around with it. It creates this way more complex system with multiple horizons and these wild regions where you'd be forced to spin along with it, whether you wanted to or not. So here's the big takeaway. Gravity isn't just about mass, it's also about spin. Okay, let's put a pin in the world of the heavy for a minute and jump over to our second path, the quantum lightweights. We are leaving the massive cosmic scale behind and diving headfirst into the realm of the unbelievably small. A world where particles are definitely not the tiny little marbles you might picture. Down at this scale, the best way to think about a particle is as a wave, like a little vibration in a field. And in this view, a particle's mass isn't about how much stuff is in it. Nope. Its mass is just the frequency of its vibration. It's really that simple. A higher frequency, a faster vibration, means more mass. A lower frequency means less. And hey, does this sound familiar? Just like with black holes, we can add a twist: quantum spin. Now, the simplest kind of quantum wave has zero spin. You can rotate it a full 360 degrees, and it looks exactly the same. But the waves that make up actual matter, like electrons, they're different. They have this internal direction to them, and you have to rotate them a full 720 degrees. That's 2 complete turns just to get them back to where they started. How wild is that? So I want you to picture the entire universe filled with these fields, a different one for each kind of particle. Think of it like a giant invisible crystal grid that fills every inch of space and time. And what we call a particle, like an electron or a quark, it's not a solid thing. It's just a tiny localized vibration in that huge grid. a single note being played on an immense cosmic instrument. This whole concept, this is a relativistic quantum field.
Okay, so we've just been through two worlds that sound completely different, right? On one hand, you have these massive, heavy objects that warp spacetime. And on the other, you have these lightweight, vibrating quantum waves. They seem totally unrelated. But what if they're actually speaking the same language, just with, a different accent?
And this right here, this is where it all clicks together. This is the moment. Look at this. In the world of black holes, mass is all about the size of its event horizon. In the quantum world, mass is the frequency of a wave's vibration. Okay? Now look at spin. For a black hole, spin is about how fast it drags spacetime. For a quantum wave, spin is about the way it internally vibrates. Are you seeing this? It's two different ways of describing the exact same fundamental properties, mass and spin. It's the same blueprint.
This isn't just some neat coincidence. No way. This parallel is the whole key. It points to a conclusion that is so deep, so profound, it could literally rewrite everything we think we know about reality. After going down two paths that seemed miles apart, this is the spot where they finally merge into one. The atoms and the subatomic particles that make you, me, this planet, everything we can see, they are not tiny little balls of stuff. According to this idea, they are something else entirely. They are, in fact, a kind of quantum black hole. Yeah, just let that sink in for a second. The smallest things in the entire universe are just super lightweight versions of the biggest, most massive things. A particle like an electron acts like a quantum wave simply because it's so incredibly light. But at its core, it shares the same fundamental design as a black hole. Everything is one. A knot, of course, leaves us with one last, absolutely mind-bending question. If the fundamental building blocks of our reality, the things that make up you and me, aren't solid little specks, but are actually tiny quantum-scale black holes, little whirlpools in the fabric of spacetime, then what does that say about the world we think we know? What is the true nature of reality? Now that's a thought to chew on. Thanks for joining me.